All right, today we're diving into one of the most fundamental forces in the entire universe. Seriously, it's this invisible hand that, keeps our feet planted on the ground, but it also holds whole planets in their orbits and shapes the very structure of the cosmos. We are talking about gravitation. Let's get right into it.
So let's start with a classic question, one that stumped people for centuries. We've all seen an apple fall from a tree, right? It just drops straight down to the ground. But then you look up at night, and the moon is just hanging out up there. So what gives? Why does one fall while the other one seems to float? Well, here's the wild part. The exact same force is pulling on both the apple and the moon. Get this, the moon is actually in a constant state of falling toward the Earth. The only reason it doesn't crash into us is that it's also moving sideways so incredibly fast that it just keeps missing. This amazing force is a universal attraction, and it connects literally every piece of matter in the universe.
So let's lock in a clear definition here. Gravitation is, simply put, the force of attraction that exists between any two objects that have mass. And when I say any two objects, I mean everything, not just giant planets and stars. That's right. Every single object with mass pulls on every other object. So yeah, the Earth pulls on the moon, sure. But that also means there's a tiny, tiny gravitational pull between you and the very device you're watching this on right now. Now, it's an unbelievably weak force at that scale, but it's always there. It's this constant, invisible connection.
Now, this universal pull isn't just chaotic or random. Nope, it follows a very specific and predictable rulebook, and we can actually calculate its strength, all thanks to something called the universal law of gravitation. And here it is. This is the famous formula that Isaac Newton worked out. You can think of it as the mathematical recipe for gravity. Now, I know, it might look a little intimidating with all the letters, but the story it tells is actually pretty simple.
So let's just break it down real quick. F is the force we're trying to figure out. G is just a fixed number, a constant that makes all the math work out right. The parts you really need to pay attention to are M and M. Those are the masses of the two objects, and D, which is just the distance between them.
So really, it all boils down to just two things. First, mass. The more stuff an object is made of, the stronger its gravitational pull. And second, distance. The farther away two objects get, the weaker that pull becomes. That's it. It's really that simple.
Okay, so let's bring this big universal law right back down to Earth, because it helps us clear up something that people get confused about all the time, the difference between mass and weight.
It is absolutely crucial to understand that these two are not the same thing. Your mass is the actual amount of matter, the stuff you're made of. That number is constant. Doesn't matter if you're on Earth, the moon, or just floating out in space. Your weight, on the other hand, that's just a measurement of gravity's pull on your mass, and that can change a lot depending on where you are.
To put it as simply as possible, your mass is always your mass. Your weight, that's just the local gravitational handshake between you and whatever big planet or moon you happen to be standing on.
And there's no better way to really get this difference than to take a quick imaginary trip to the moon. Let's see how this whole concept plays out in the real world.
1/6. Just remember that number, 1/6. So what does it mean?
It means that your weight on the moon would be just 1/6 of what you weigh here on Earth. Now, your mass, all that stuff you're made of, is exactly the same. But because the moon is so much less massive than the Earth, its gravitational pull on you is way, way weaker.
And this table right here, this really shows us the why behind that 1/6 number. Just look at the mass column. The moon's mass isn't just a little smaller, it's more than 80 times less than Earth's. That huge difference in mass is exactly why its gravitational pull feels so much gentler.
Okay, so we've established that gravity is this constant downward pull. But that brings up a new question, right? If gravity is always pulling everything down, then how come some things, like a boat or even just an ice cube in your drink, float? Well, it turns out there's another force in the mix, a rival force. Whenever you put an object in a fluid like water, the fluid actually pushes back. So it's this constant battle. Gravity is pulling down, while this upward force called buoyancy is pushing up. And this upward push is described perfectly by something called Archimedes' principle. All it says is that the buoyant force pushing up on an object is equal to the weight of the water that object shoves out of the way. So, if an object displaces a bunch of water that weighs more than the object itself, it's going to float.
This little experiment is a perfect way to see it in action. See? In the air, the stone weighs 0.67 newtons, but once it's underwater, the scale reads only 0.40 newtons. That missing 0.27 newtons? That's the buoyant force. That's the water pushing up and making the stone feel lighter.
So ultimately, the winner of this whole tug of war really just comes down to one thing: density. An object that's less dense than the fluid it's in, like this cork, is going to float every time. But an object that's more dense, like an iron nail, well, it's going to sink, because the downward pull of gravity on it is stronger than the upward push from the water it displaces.
So we've seen how this one incredible, invisible force, gravitation, governs everything from a simple falling apple to planets orbiting a star. But it's really just one piece of a much larger puzzle. So the question I want to leave you with is this: what other invisible forces